Everyone. Move this stuff over. Good. All right, so today we are going to cover Thompson's 8.3, which is the electron quark scattering section. So previously in the previous video, right, we kind of changed the Rosenbluth formula, right, into this format of the structure function where, basically F2 is kind of quantifying the electro, the charge and the magnetic coupling between the electron and the stuff inside a proton. And then, right, F1 gives you the purely magnetic coupling. Okay. And we did all of these, change of variables. We defined all these new kinematic variables, X, Y, and V. And then, right, you might think, like, what's the point of all this? Okay. What we're going to do is the next two sections, actually, we have to get through 8.4 also. And at the end of 8.4, that's when the magic happens, where we're going to be combining what we learned from 8.2 to what we're going to learn in 8.3 and 8.4. So I'm going to try to make both of these lecture videos tonight. Okay, so what we're going to do is we're going to model, right? We're kind of in this little regime here, right? And notice that, when this electron comes by, you're actually scattering off one of the constituents of the proton. Okay, and since the quarks inside the proton are the only ones that have an electric charge, gluons are neutral, right? Well, electrically neutral, has a strong charge instead. Okay. What we can do is we can actually also use quantum electrodynamic to compute the electron quark scattering. Okay. Just as before, right? If you have some particle with a charge coming in, electron in this case, and a quark coming in, this is the kinematic diagram, right? Where you have these two colliding together, and then they scatter off each other, and then the electron is the one we actually measure, and it comes off at some angle, theta. Okay. Okay. The Feynman diagram for this, right, is just two electrons, an electron scattering off a quark. Okay, this mu is the Lorentz index mu, so be careful, right? And then this is the Lorentz index nu, and the exchange of photon between them, right? So this Feynman diagram has been calculated to death for us. But what we're going to do is we're going to use the Lorentz, the frame-independent version of the matrix, Lorentz invariant matrix element, MFI, right? And we're going to take the results from, I think this is from chapter, actually from chapter 6, where they cover the trace method, which we skipped, okay? It's just a really useful method if you're doing a lot of these calculations, but, right, hopefully we don't have to do too many of these in the future. But what we're going to do is we can actually just use the result from that section, okay? So the result from that section is that the Lorentz invariant matrix element, okay? In that case, I think we're just doing the charge of electrons and muons, so that will have a charge factor of 1. But in this case, right, since we're going to be scattering off quarks, which has fractions of electric charge, right? So the up quark has a charge of 2/3, and then the down quark has a charge of 1/3, right? So we actually have to account for these factors in here, okay? The result from that is that, it's just going to be S squared U squared divided by T squared if you're scattering off this T channel process. Okay, so this is T channel only. Okay, right. Well, S, right, is P1.P2, and then U is P1.P4, and T is the momentum exchange between the two, and it's actually P1.P3. Okay, so in terms of these 4-vector dot products, now what we can do is that, well, we can use figure 8.5 left, right, to basically determine all these 4 vectors, okay? We're going to be in the limit where, well, the energy is much higher than electron mass and also the quark mass, because that's going to be much less in this case in order for us to probe inside the protons anyway, okay? So P1, right, simplifies to just the energy of the incoming electron, okay? P2, right, is the energy of the incoming quark, right? But since they're going to be colliding together in the center of mass frame, right, in the center of mass frame, they're going to be equal and opposite each other, right? So therefore, they are the same, except that the momentum along the z direction is negative in that case, okay? When these things scatters off each other, okay, we're going to be scattering off the z-axis, right? You'll gain some x component for the electron, and you'll get negative of that for the quark, okay? And then you have a fraction of the momentum left in the z direction quantified by cosine theta, okay? Okay, so what we can do is compute all these dot products to get P1 dot P2, right? That's just going to be E squared, and then P1 dot P3 is going to be E squared 1 minus cosine theta, and then P1 dot P4 is E squared, but with a 1 plus cosine theta, okay? And these little star signifies is this in the center of mass frame, right? Okay. All right, so plugging all of this into the matrix elements, what you end up with is this long equation where you have, the fraction of the quark charges. That's going to be important, right? Depending on which one we have. And also we get, 4 times the energy to the 4th power. And then you have these cosines dependence on the denominator and numerator, okay? All right, so what we're going to do is we're going to plug this Lorentz invariant matrix element into, right, the differential cross-section that we calculated in chapter 3, all the way back to chapter 3, right? Where, for any process where you're scattering, 2 particles with each other through the T channel, the differential cross-section in a center mass frame is just going to be the matrix element square times the ratio of the outgoing and the incoming momentum of one of them divided by the center mass energy, and there's a 64 pi square, okay? In this case, PF and PI is in the high energy limit, which is going to have this is just going to be 1, okay? Okay, and then factoring out the factor of 4, right? And plugging in the Lorentz invariance matrix elements, oops, went too far, right, into MFI square here, right, you're going to end up with equation 8.15, which is that the differential cross-section is proportional to Q, the charge of the quark squared, right? The charge of the electrons, well, the elementary charge to the 4th power, because the quarks is also proportional to E, and then the electrons proportional to E, so you get 4 factors of that instead. We leave this square root S on the bottom. Some of the factors of the 64 canceled out because we factor out a bunch of stuff from the from MFI, okay? But then you still have this 1 plus 1/4 1 plus cosine theta square, and then you have these 1 minus cosine theta square on the bottom, okay? So these terms in the numerator is really worth discussing because it really harkens back to what we learned how to do in chapter 6, right? Where we have these spin sums, helicity sums, okay? So the first term, right, this 1 here, right? Well, this 1 is really not just 1, right? It's 1 divided by 1 over cosine squared theta times a bunch of stuff, right? Okay, this is the term where both the electron and the quark actually just retain their original helicity directions, okay? Right, so what I mean by that, right? So this term is contributing from these 2 diagrams here, where you have the quark coming in, the electron coming in, the quark coming in, and the electron, right? Let's say it was, since the momentum is in this direction, P1, right? The helicity, if it's the same direction, that's a right-handed helicity electron, right? And then the momentum going out, P3 is here, and then the helicity and the momentum is in the same direction. That's also a right-handed helicity electron, right? In this case, what you're doing is you're actually scattering a right-handed electron and then a right-handed quark off a right-handed electron, and then the final state turns out to be right-handed electron, right-handed quark. So the helicity of the quark didn't change. Okay. Right. Similarly, you can do the same thing with the left-handed, where basically the arrow just point opposite direction of the momentum. Okay. In this case, right, what's happening is that the angular momentum of the electron quark system together, right? Okay, since they're going opposite direction of each other, right? Basically, their angular momentum is actually zero. Okay, so and so in this case, right, you don't have any angular dependence because, right, since the angular momentum is zero, there's none of this, spin coupling thing happening. Okay, but the second term, this one right here, right, is our usual, right, 1 plus cosine theta, the whole thing squared, okay? This is where the helicity state actually swap between the two, right? Where you have RL, let's say, right? And then that's actually going to be swapped to LR, or if you started with LR, it swaps to RL, okay? In this case, right, the electron quark system actually have a total helicity of either +1 or -1, depending on which one we're talking about, right? Okay. And in that case, right, you do have this angular momentum coupling in the system, and therefore, right, this is the reason why you end up with a high probability of the electron basically going in a straight direction, so where it minimizes the scattering angles. Because where you notice this, right, if you put in 1 plus cosine theta, right, if you put in theta equals to 0, then this factor goes to 2. If you put in theta equals to pi, this factor goes to 0, right? So they tend to want to go in the forward direction, meaning they don't scatter off each other that much, right? For them to bounce off each other is almost impossible. Okay, so that's sort of the more physical interpretation of what the cross-section is doing. It's very similar to what we saw in the electron proton scattering, where we're still outside the proton and we're not scattering off the quarks inside. Okay, all right. So we're going to do a little bit more kinematics. Okay, so if we want to write q squared, which is actually in this case, since it's a T channel process, the q squared is T, the Mandelstam variable, right? So q is just P1 minus P3. Okay, since you squared it, you square this. Okay, what happened is that when you do this computation, you're going to end up with, basically P1 squared. I'll just write this out over here, right? P1 squared plus P3 squared minus twice P1 dot P3, okay? And this dot product is going to give you this 1 minus cosine theta thing, right? And then the magnitude of this, since they're e's, right? So you'll have this e out here, and then the minus sign just comes from the negation, okay? So q squared is basically going to be, well, what was the point of this, right? So this is the mass of the electron squared. This is the mass of the quarks. But actually, this is still the electron squared, right? Since these are pretty small, right, you can just approximate them to be 0. So there's sort of this little squiggle sign. And therefore, right, we can actually write the cross section right up here, right? Okay. Up top here, right? in a Lorentz invariant form because, right, we know that this 1 minus cosine theta thing is also down here. Okay, massaging the equation a little bit, and I'll have you guys do this in the homework. You can write the differential cross section, right? Instead of writing it in terms of theta, you can write it in terms of q square. Okay, where you're just changing this variable from theta to q square. So now the differential cross section is actually in this Lorentz invariant form of d sigma dq square, right? And you'll fill in the algebra step to show that this is actually true.